Welcome to the Dinosaur George podcast, a show about paleontology and other earth sciences. Dinosaur George is a public speaker, author, and TV host with 30 years of study in paleontology. He has performed live in over 4,500 events across the US and Canada. Now, here is Dinosaur George.
Hey there, good afternoon or morning or evening or night, wherever you happen to be. This is Dinosaur George, and you're listening to podcast number 105. In this episode, the featured creature is Psittacosaurus, the little early ceratopsian. With us to talk about Psittacosaurus and some brand new science behind a new discovery is Dr. Michael Pittman from the University of Hong Kong. He's got some really cool information, real high-techy stuff. So sit back and relax. This will be a fun ride.
It's time for our Feature Creature segment. If you would like to suggest a creature, go to dinosaurgeorgepodcast.com and post it in the comments section of this episode. Or email us your suggestions to contact@dinosaurgeorge.com. And now, our feature creature.
Our feature creature for this episode is Psittacosaurus, which is a little ceratopsian. Its name means parrot reptile. The reason why it got that name is it has a very distinctive parrot-like beak. And in fact, all members of the ceratopsian family share that one particular feature. So when you look at it, you instantaneously recognize it as a member of the ceratopsian family, even though nothing else about Psittacosaurus looks like some of its ancestors. These little dinosaurs are bipedal, meaning they could walk on two legs instead of four. Some suggest that they walked on all fours. In fact, when you see pictures of them, oftentimes you see them standing on all fours. But I remember reading somebody's study that suggested that they were incapable of walking on all fours because of the length and the configuration of their arms. So for me, I believe they were bipedal, but I could be wrong. Now, they're herbivores, so they definitely are plant eaters. Their little parrot-like beak and their little teeth are perfectly adapted for eating the tough, fibrous vegetation that grew in their environment. They weren't very big dinosaurs. They grew to about 1.5 meters, which is about 5 feet in length. And the adults weighed about maybe 20 kilograms, which is like 44 pounds. So again, these are not really big dinosaurs. But they're cool looking. They're the earliest member of or one of the earliest members of the ceratopsian family. When we say ceratopsians, we're talking about Styracosaurus, Triceratops, Protoceratops, all of those guys. And again, when you look at them and you see that beak, you can understand the relationship. They appeared in the early Cretaceous period, about 123 to about 100 million years ago. So they were some of the earlier members of this family. There's 11 different species of Psittacosaurus known. Now, when we say species, what that means is all dinosaurs have a first and last name. The species name is the last name. So the genus is Psittacosaurus, but then there are 11 different dinosaurs that share the name Psittacosaurus. So there's 11 different individual species within that group. They've been found in Mongolia, Siberia, China, and maybe even Thailand. There's some evidence that they may have even lived in Thailand. Psittacosaurus is one of the most completely known dinosaur families ever discovered. And what I mean by that is literally hundreds of individuals have been found. And this includes from hatchlings, from newborn little babies, all the way up to adults. And since so many skeletons are found and so much evidence is available to paleontologists, it allows them to do several really detailed studies about Psittacosaurus's growth rate and reproductive biology. So that makes these dinosaurs incredibly well known. Now, although these early members of the ceratopsian family are well known, a recent study has given scientists some insight into one of the more unusual features of this dinosaur and others. So here to tell us about it is research assistant professor and the head of the Vertebrate Paleontology Laboratory in the University of Hong Kong, Dr. Michael Pittman. Dr. Pittman, welcome to the show.
Thanks. Welcome. Thanks very much.
You bet. So it's sort of customary for us to kind of ask a little bit about yourself. Can you tell us a little bit about you? You're obviously in Hong Kong, so tell us a little bit about your history, your education, and such.
Sure. So I actually grew up in Hong Kong because my mother's from there, and my dad's actually from the UK, and in the UK is where I did my university education. And as luck would have it, I ended up moving back to Hong Kong, where I'm working at the University of Hong Kong now. And I've always actually liked dinosaurs. As a kid, I've found them, really inspiring and cool. And then that kind of led me to do geology as an undergraduate. And then I realized that there were professors that study dinosaurs. So when I found that out, I set off on my path to become a dinosaur professor myself. That's
it's so amazing. Almost everything that every paleontologist I've ever met always has two loves. One is dinosaurs, regardless of what branch of paleontology they study, they love dinosaurs. and it's always something that was inspired when you were young. It's seeing a skeleton. Yeah. So it's those are the two factors that sort of tie everybody that likes dinosaurs has those connections.
Well, I'm hoping that some of our listeners might end up being paleontologists in the future, hopefully.
Boy, how nice would that be? That would be. So, now, do you get an opportunity to do field work? Obviously, your part of the world is a hotbed for new discoveries. Do you get the chance to go out into the field very often? Yeah, I do.
I love the field component. So having done a geology degree where you spend a lot of time in the fields, my research now, that's a major component. So I would say that I'm a field paleontologist, and where I do my field work, it kind of varies from time to time, but mostly it's in the Gobi deserts of China and Mongolia. So it's a very, very hot part of the world in the summer, kind of just like the deserts in the United States. And in the winter, it's one of the coldest places on the planet.
Wow. So are you limited then to when you can do your field work?
Yeah, professors usually are free in the summertime when the students have their holidays, big holidays. So unfortunately, we have to go when it's the hottest time of year. But I quite like it. I quite like desert. It's very peaceful. The mobile phones don't work very well, so you can kind of disconnect. And we go there because we have huge, vast expanses of rock formed during the age of dinosaurs. And to give you an idea of some of the places that we go, some of the rocks have yielded fossils such as Velociraptor, that famous carnivore, and also a gigantic beak dinosaur called Gigantoraptor.
Oh, wow. Wow. Well, I guess the most fascinating thing to me about what we see here, what the discoveries that we find out about here seem to recently have one thing in common that at one time I don't think paleontologists ever dreamed we would find until, of course, they found Archaeopteryx. So what sort of oddities are you finding in some of the specimens out there?
Well, I think we've always found dinosaur fossils as bones. At least we start off finding them that way. And, finding fossils like Archaeopteryx with feathers, so that's more unusual. But, being in China, I work a lot on feathered Chinese dinosaurs, so I'm slightly biased because most of the fossils that I study preserve skin. If they're theropods, they preserve feathers. And in some of these dinosaurs, we even have evidence of their coloring. So, these kind of exceptional fossils are kind of very rare. But there are lots of gaps still in terms of, what can you find in a fossil. We have fossils where you preserve the eyelid. You preserve the intestines. You preserve the stomach area. But like, for example, fossils where you can confidently say that you can see the heart or the liver, we haven't found yet. So actually, there's bits of dinosaurs where we still have question marks, and I find it quite exciting to find those, because then you can understand more about how their body worked.
That's absolutely fascinating. I wonder, when you were starting out, had those things started to be discovered when you started your education, or was that relatively new, something that was sort of cutting edge that nobody had ever heard about, is all these different things?
Well, in terms of dinosaurs, when I was a postgraduate student, they had already been finding all these like feathered theropod dinosaurs, as well as scaled non-theropod dinosaurs. So that had been going on for a while, but it was still like a gold rush for those kind of fossils. So when I kind of got into things, it was very much in the thick of it. And at that time, lots of people from all over the world were kind of centering on China to study these amazing fossils. But having said that, it's not, even though it's a hotbed, there are other places, for example, in Brazil, the Santana Formation, we call it, and other very exceptional areas where you preserve fossils that paleontologists have been studying. But being slightly biased studying a lot there, but I still think that this is probably the place if you want to find out about the soft tissues and the skin of dinosaurs. China's number one place.
So all the feathered dinosaurs we know of, are that when I say we, I'm talking about like people like myself, that we love dinosaurs, but we don't necessarily have same access to information that you do. We always see them as they have two things in common. They're small and they're carnivores. So is that pretty much the rule?
Well, the feathered dinosaurs are a group of dinosaurs called the theropods. So they include Tyrannosaurus, Velociraptor, as well as birds. So those animals were two-legged, but they had actually quite a variety in size. If you think of an animal like T-Rex, it's massive, the size of a bus. And then you get the tiniest of birds that could fit comfortably within a teacup. So those animals, were mainly two-footed, although some, the jury's out, may have actually spent time on four legs, could have spent time on four legs, but that's kind of still contentious. So yeah, they were definitely two-legged, but they actually varied quite a lot in size. Wow.
And so do we know where feathers come from? What is the material that, where in the fossil record do they show up? Do we have any idea?
Sure. That's an extremely good question, because when I was a child, and it would have been the same when you were a child. Most people saw dinosaurs as these scaled animals, and if you were a scientist that subscribed to the hypothesis that birds were a type of dinosaur, then you had these weird birds that had feathers. And then in the 90s, we've been talking about feathered dinosaurs. In the 1990s, that's when we start to see these feathered dinosaurs pop up. And, we've got dozens and dozens and dozens of species of them. And they include birds themselves, but and these, as well as other animals that appear more like animals like T-Rex. They have a long tail, and they most likely wouldn't have been able to fly at all. And those fossils basically solidified beyond any reasonable doubt that birds are a type of theropods, and they are, in fact, a dinosaur. So at that point, in the 1990s, suddenly dinosaurs were mostly scaled, but there was this big group of them called the theropods, which included the birds, which had feathers. And then in the 2000s, we found some really cool fossils that really cast new light on dinosaur skin. So, at the end of the 1990s, we know that a lot more dinosaurs were feathered, but these feathers, they look very similar to ones that we see today, but they also include structures that look much, much simpler. Some which were, less complex, and some which were actually more like human hair in their appearance. So people developed a kind of a hypothesis of how feathers evolved by becoming more and more complex. And in the 2000s, in other dinosaurs, in the ornithischians, the complete other side of the dinosaur evolutionary tree, we find these hair-like structures in 3 species of ornithischian. And these are slightly different because they're generally a bit coarser. And but from the details that we had, it raised an amazing possibility that these kind of like hair-like primitive feathers were like an ancestral condition in dinosaurs. Now that kind of hung in the air because, without knowing more details about these ornithischian hair-like structures, it was kind of difficult to take this idea further. And that is where my study comes in, this recent one with some colleagues in Germany, in the UK, and in the United States. And what we did is we looked in much more detail at the tail bristles, the hair-like structures on the tail of Psittacosaurus.
So when you're talking about ornithischians, you're talking about plant-eating dinosaurs now.
Yes, exactly.
So all along, this notion that dinosaurs and birds are related has always been, but related to the theropods, the carnivorous version, and there wasn't there wasn't any sort of link with the same featherish structure. I guess, is it keratin? Is that what the basic component is? They're kind of So now we've got evidence, which is the subject of today's episode, which is Psittacosaurus. You now have identified, or science has identified, now the plant-eating side of the family tree to also having this. So can you talk a little bit about your findings with the study?
Sure. So the structures themselves, these tail bristles in Psittacosaurus, are slightly different. They're a bit thicker than those hair-like structures that you would get in the theropod dinosaurs, and they have, some interesting kind of surface texture. So that was really all we could see up until this point. But what we did is we used a new cutting-edge imaging technique that I've been using to study fossils in collaboration with a colleague in the United States, Thomas Kay. And he develops a method where you shine a laser at fossils, and what happens is the laser light goes into the fossil, and it goes in with a certain color. We actually use a kind of bluish-violet laser. Doesn't damage it, but it goes inside, and when it interacts with the fossil, it loses some energy. And when it does that, the light comes out of the fossil again with a different color. And when that happens, that part of the fossil is said to fluoresce. So what we did is we shone the laser at our specimen and reassured the curator of the fossil, which is located in Germany, that we weren't going to fry their precious fossil with our laser. And having done that successfully, we managed to find that parts of these bristles were fluorescing. They were fluorescing with a very specific pattern. We found that centrally they had this kind of hole in the middle, or what appeared to be this hole in the middle that ran through them. And we hypothesized that this is what we call a lumen. And so it seemed that these were just like hollow shafts, these tail bristles. And we took these observations and we kind of scratched our heads. We're like, wait a minute, we don't really, we're not very sure if we see those in theropods, because in the theropods they're usually preserved as kind of a dark film, and they usually don't fluoresce with the laser, and so we can't really see what their internal structure is. So what we did is we compared it with modern birds, and we find that these bristles look similar to a number of modern bird species. And these structures, rather than being on the tail, all appear on the head. So one of them is called a turkey beard, and that's like it basically looks like a horse's tail stuck on a turkey's neck, and these are like long, kind of thin hair-like structures. But crucially, they're not true feathers. True feathers, they must grow out of a follicle, like a little indentation in the surface of the animal. So they don't do that. These bristles in Psittacosaurus are also similar to two other bird structures. So one is the spine on the head of, and this is a funny name, the horned screamer. And this animal, really peculiar. It has this spine sticking out, and this structure is also similar to what we found. And the third animal is called the Congo peafowl. So it's very closely related to the beautiful peacock. And rather than having a spike, it has basically a turf of these kind of bristles on its head, and it kind of looks like a punk rocker. It kind of sticks up on its head, and so what we find is when we look inside, in particular, if we look inside the horned screamer spine, we find that it also has this central pulp, the central region in the feather that goes up through it. And because it had such a striking similarity with our tail bristles, it got us wondering, because just like the turkey beard, both the horned screamer spine and the bristles on the Congo peafowl, they're also not true feathers. They don't grow out of a distinct follicle, a hole in the skin surface, even though they're made of similar materials to true feathers. So that got us thinking, well, if these aren't true feathers, then maybe what we are seeing in Psittacosaurus isn't a true feather that we're seeing in these kind of birds and in some of these theropods that are not birds but have feathers. So that really kind of threw a spanner in the works, because if we found them to be super, homologous, they're basically the same thing as true feathers, we could have this beautiful story where actually all of the dinosaurs, they start off with true feathers or something related to true feathers, and then they went about their own way and evolved in different directions. But because these structures aren't true feathers, it kind of raises questions about, how are these structures related to true feathers? Are they actually the same thing? Do they actually, when they develop, when they evolve, did they actually start with these these filament structures and evolve into true feathers? What actually happened? So as a result of this paper, we're kind of supporting a recent study which used statistical methods to actually show, what is the ancestral conditions for dinosaurs. And what it does show is that it appears that in the first dinosaurs, they didn't have structures on their body that we would basically call feathers. So we can say that, the first dinosaurs were scaled, and whether or not they had these bristles or structures that are actually related to true feathers, we still don't know.
Wow. So for the listeners that have not seen the updated image of now what they believe Psittacosaurus looked like. Can you sort of give a description of what these bristles are that we're talking about, where they'd be found on the body, sort of an idea for them?
Sure. So in Psittacosaurus, they're found on the tail, and they're quite wide. They're maybe half a centimeter wide, and they get up to maybe 20 to 30 centimeters. Unfortunately, in there's only one Psittacosaurus that preserves these tail bristles, so we really don't want to lose that specimen.
Sure.
And they're actually cut off at the end, so we don't know the total length of the bristles, but they were probably at least more than 20 cm long, and they seem to not be that stiff because they actually curve round in the same way that your hair doesn't stick up because it's not completely stiff. These bristles kind of curved along the tail, and they seem to be only in one portion of the tail rather than the whole tail. And because the specimen is so well preserved, we actually preserve the scales all over the body of this animal. We're pretty confident that it's limited to the tail. Now, moving on to the other ornithischians that have these kind of hair-like structures, in a more primitive, earlier ornithischian, it has these structures at least on the tail, back, and on the neck. And I say at least because the fossils that we have that preserve this aren't perfectly complete, so they may have actually been covered in them. But they were much, much thinner, so they were maybe 1 or 2 millimeters thick, and their length, kind of, it was a smaller animal, but they were kind of on the magnitude of, maybe 10 centimeters, up to 10 centimeters or around there. And then we have a third dinosaur, which was the most recent find, and that was found in Russia. And that is from an animal that's in the kind of middle of the ornithischian tree. So we have 3 examples of these kind of hair-like structures in 3, in the base, in the middle, and towards the top of the ornithischian tree. And in this Russian example, they vary in length, but the really interesting thing is that some of them appear to protrude from the center of the scales, and that kind of raises questions whether they're growing out of a follicle, and because as I've mentioned before, if that happens, if these structures grow out of a follicle, then it means they're actually a true feather. So this fossil is kind of particularly interesting. So what we're actually hoping to do is extend the method that we've used in Psittacosaurus to these 2 other animals. The one from the primitive ornithischian is actually called Tian Yulong. It's another Chinese specimen. And the third one, this Russian specimen, is called Calindra dromaeus.
Wow. So let me ask you, could it have been that the ornithischians and the saurischians are both, there's sort of a convergent evolution going on with these structures? It's just one group has more of what we think of as feathers, and maybe the ornithischians that you're describing, is theirs maybe a more advanced or lesser advanced version?
Yeah, absolutely. So I think at the moment, especially with our new paper, because we're not seeing, we've made this distinction that the structure we have in Psittacosaurus looks like structures in birds that are not true feathers. They don't grow from a follicle. So what that kind of suggests is perhaps they are convergent. But really, I think at this stage, because obviously, we want to get to the bottom of this, where we have to be cautious until we get more information. So I think, once we complete, studies such as using LSF for the other 2, for Tian Yulong, for Calindra dromaeus, I think then we'll have, having covered those bases, I think we can probably answer that question, with more conviction, and hopefully we can find more of these fossils. Psittacosaurus is known from hundreds of specimens, yet we only have one that has bristles.
Wow.
So what is this? Exactly. So what is this telling us about this animal? We have them at all different growths, all different sizes. Babies that have just hatched to adults. The one with the tail bristles is actually one of the largest Psittacosaurus found. So and the bones, the way they're kind of laying in the sediment, because we don't want to take the bones completely out of the rock, because that would basically destroy all the scales, the beautiful scales covering the body. We don't actually we're not absolutely sure what species of Psittacosaurus. So this may actually be a unique species of Psittacosaurus, and that other Psittacosaurus don't have it. We simply don't have much data from these tail bristles. So I think, at the moment it seems like, saying this cautiously, it seems like that, they don't seem to really be, we shouldn't really be calling them, I should say, we shouldn't really be calling them feathers, what these structures that we're seeing in Psittacosaurus, that we're seeing in Tianulong and Calindrosaurus. But I should add that the closest relatives to Pterosaurs, at least agreed upon by a great number of paleontologists, the closest relatives are pterosaurs. And pterosaurs, as you know, are these flying reptiles that include, pterodactylus, amazing animals. These animals, believe it or not, are also preserved with feather-like structures. And these are found also in these exceptionally preserved deposits in China. And I'm actually working with some colleagues in China and in the UK to try and use LSF to look at these bristles in pterosaurs in more detail. Because if pterosaurs are kind of outside of dinosaurs, but the closest relatives, if these structures show striking similarities to what we see in ornithischians and in theropods, that could really kind of push things along. So it's a very exciting time in terms of finding out what was dinosaur skin like, throughout their history from the start until most of them became extinct.
So if you do your laser test, and I got to tell you, when you were describing shooting that fossil with that laser, all I can picture is you standing there with a monocle and a cat next to this laser, saying, "No, trust me, nothing's going to happen to your specimen."
Yeah, it's tricky, because I think science fiction movies as usually, lasers usually involve cutting things in half, right, or setting things on fire. So it wasn't a good starting point. I guess what helps, well, the lasers that we use are dangerous. So, we have to fill in a lot of paperwork and fulfill, all our university's requirements for safety.
Sure.
So actually, to give you an idea about these lasers, if I took the laser and shone it on a piece of paper. So I should add that when we use the laser, we put a lens on it that actually makes the light more spread out. And because it's more spread out, the laser is less powerful. So if you think about like a flashlight, the light gets spread out. It's not as intense. That's how we use the laser when we study these fossils. But if I use the laser which wasn't defocused, which didn't have this special lens on it, then I could set a piece of paper on fire. So we wear protective glasses so that we can maintain our eyesight, and but in terms of with the goggles, with the lens, we're in a room that's locked and has a special sign on the door. We're perfectly safe, and more importantly, the fossils are safe.
Right. So if you're able to run the same test on the feather-like structures on pterosaurs, and if you can get similar readings, would that and obviously this is all hypothesized, but would that suggest then that that structure you found on Psittacosaurus would be the same basic structures that perhaps these pterosaurs have?
Yeah, so with the laser, what we're doing is, I mentioned that it's fluorescing stuff, and you can see details inside. But with the pterosaurs, for example, and with most of the theropod feathers, they're actually preserved as a kind of carbonaceous film that doesn't fluoresce. So the way we get information from them is the laser actually lights up, it fluoresces the rock that's the matrix, the rock that's holding the feathers, holding the filaments. And that kind of acts like a backlight to kind of show the silhouettes of the fossil, and that actually provides it basically reveals a lot of extra information. And so what we're hoping, with the pterosaurs, with studying the other ornithischians, is to see, finer details of those structures and try and compare those with what we can see in the theropods' feathers. And, it really depends on if we can see the details we have to compare. Because at the moment, most of the kind of relationships between these things is based on the kind of shape and the size of these structures, rather than microscopic details. So really, the holy grail for this work is to find really kind of fine details, or as we have with the Psittacosaurus, internal details.
Wow. So we're always taught that when a dinosaur dies, the skin, the muscle, the soft tissue all decomposes. How is it that what was the condition that allowed this one specimen to retain those bristles? And you're also saying that there's also scales on the skin, right?
Yeah.
Wow. So what was the condition that did that?
Yeah, I mean, these fossils are amazing. All I could, I was in Texas last year for a conference, and I managed to see a lot of the state and take in the scenery. And in Texas, everyone's familiar with animals being run over on the highways, armadillos or whatnot. All I can say is this Psittacosaurus basically looks exactly like one of those roadkill. It's as if it happened yesterday, or just in front of you. It's truly, truly amazing. I mean, obviously it's been squashed under, huge amounts of rock above it, so it's flattened. But to get that kind of preservation, you have to make it extremely difficult for the normal processes of decay to happen. And so in northeastern China, where this fossil was buried in the early Cretaceous and then was preserved until today, it was actually preserved in a very, very fine kind of mud rock. So tiny, tiny rock particles that you can't see. And this mud also contains a lot of ash. And the reason is because this animal died in a volcano influenced environment. It basically died at the foothills of volcanoes. So a combination of the mineral properties of the ash, but also getting buried very rapidly by this mud that's was washed off from a volcano, allowed it to basically get completely shut off from the outside world, shut off from the air, so that it couldn't decay as it would normally do on the surface. So that's the key thing. And when these animals die, the bacteria that were in their bodies and also in the sediment itself, they interact with the sediment, and that actually, believe it or not, helps to create conditions that further promote preservation.
Wow. And then also scavengers and predators would have been driven
can't
from
get
the
to them.
area.
Exactly. And I mean, if you're buried, no one's going to go in and go in and get you.
Right.
And in some of these, some of them were clearly like died and were swept into a lake, and most of these are actually found in lake deposits. So the mud, the animal was washed in with the mud into a lake and covered up very quickly. As these various eruptions happen. Sometimes we actually have them preserved in lahars, and lahars is what happens if you look at kind of videos of Mount St. Helens eruption, or eruptions in one example is in Mount Pinatubo in the Philippines. When you have eruptions that have a lot of ash and it settles, and then you have rain, you have these torrents of muddy rivers that basically swallow up everything in its path, and cause a lot of trouble and a lot of sadness to people around the world in different places today. They cause a lot of trouble for the dinosaurs, and we have examples where dinosaurs were swept in these rivers of sediment and then buried.
Wow. So, since you're unable to extract the bones from the plate, because you said it would, of course, ruin the most important part, which is these bristles in the skin, do you have any way, from what you can see, of determining the sex? And do you think that these bristles would have been associated with one sex over the other?
Yeah, that's a very good question, because I mentioned how it's found on one of the biggest Psittacosaurs. It's only found on one, even though we actually have a handful of specimens that actually are covered in scales. So we're not sure if this belongs to a unique species, but because we only have one, and we're not really sure if this one is a similar species to other. These handful of Psittacosaurs that do have beautiful skin preservation, scale preservation, we don't really know at the moment if it's a male or female thing, and that's something was really interesting, because people have if you look at modern animals today, whether it's the horns on sheep and things, various animals today, they have different ornaments that are and aren't present in the male and female. So like, the beautiful frond of a peacock is actually from the male. And we really don't know that at the moment for Psittacosaurus, just because we don't have enough specimens. And that's the same thing for the other two ornithischians. In theropods, though, because we have dozens and dozens of species and hundreds of specimens, we definitely do know that not just in birds, but in non-avian theropods, in these kind of closest theropod relatives to birds, we actually have feather arrangements that seem to show differences, like two modes. And so one explanation is that represents a female-male mode. One other explanation could be that maybe this is something that changes as the animal grows. But I think, definitely for ornithischians, at least in terms of their bristles, we don't know yet.
So can you hypothesize what the function of the bristles would have been? I realize that's a tough question.
Sure. Yeah, no, it is. Like, I mean, we're lucky today that we can go to zoos and look outside the window and see birds and how they can have different body covering and have like different display structures, et cetera. With Psittacosaurus, we can't go back in time, but because it's found on the tail and they're quite prominent, one kind of obvious possibility is that they were display structures. If this was, for example, on a male, it could have these structures to say, "Oh, hi, I like you. Let's have babies." That's one possible function. The other one is it could be like a structure of intimidation. Perhaps it does actually make the animal look bigger. It makes the silhouette of the animal bigger. Maybe by having it makes the Psittacosaurus look bigger, and that's kind of wards off would-be predators. So that's another reason. In theropod dinosaurs, these kind of hair-like structures, because they're much thinner and much densely packed together, they kind of, in some cases, really look like a tuft of hair, like on our heads. They've been suggested to have maybe perhaps an insulation role, but in Psittacosaurus, the bristles are actually clumped in bundles. You have maybe a handful of bristles clumped, all clumping towards the same point in little clumps along the tail. And because they're so thick and there's so much space between the bristles, I find it difficult to think that they were used for insulation. But maybe they were. So I mean, those three possible functions I think are the most likely. But unfortunately, with fossils, we may never know with Psittacosaurus.
Sure. So in feathers, even in, if I understand even the earlier feathers, it has a center, I don't know what the term is, but a center section with all of the branches coming off to form the feather. Are these bristles like that?
So the feathers, they have a rachis, that central vein, and that vein is hollow inside. So what we've established in the Psittacosaurus paper is that we think we have this kind of lumen, like a similar kind of structure in the middle that presumably was filled up with a pulp, and that's what we see in these birds like the horn screamer and the Congo peafowl. So in that sense, as with the central, like a kind of shaft-like structure with a hole that may or may not have been filled, that part of the feather is similar to what we find in the tail bristles of Psittacosaurus. But this key difference is how the true feathers, they come from this follicle. So, we have something in our hair. Our hair is attached to something which is called a follicle. And the same principle applies, with birds and theropods. It's basically like a little indentation into the skin surface where the structure goes in. We have that. That is found in true feathers, but not in these spines of the horn screamer, in the bristles of the Congo peafowl. And because in the paper we're kind of trying to say that amongst modern birds, those two examples in particular are the closest analogs to what we see in Psittacosaurus. We're kind of basically drawing a distinction between the true feathers, which seem to be what we have in the feathered dinosaurs, and as well as primitive versions of these true feathers. We're trying to draw a distinction between those and what we see in Psittacosaurus.
Wow. So let me ask you, and again, this may not even be available in the fossil, but is there any indication that the animal would have the ability to raise and lower these bristles, sort of like the way a cockatoo can raise that group of feathers on its head? Could you think they could do that?
That's an excellent question, because modern birds have, very, complex like muscles that they contract and relax to actually, move the feathers relative to the body surface. So that happens, that kind of muscle system you find in all birds, and different birds can use it more effectively than others. So you mentioned the cockatoo, but actually, with the wings and stuff, a lot of the movement of the feathers, you're relying on some muscle movements to actually, move the feathers relative to the kind of skin surface. So in Psittacosaurus, because we're saying that they look most similar to, the horn screamer spine, to the bristles in the Congo peafowl, because these guys don't have this follicle, then they don't also have the same muscular system that's used to kind of control them. Yeah.
Right.
So that I think, and with the spine in the horned screamer, to my knowledge, it doesn't move. It just waves about because it's not perfectly stiff. And same with the bristles; they don't really do much. And in the turkey beard, I mentioned that example. It's kind of like a horse tail on the neck of a turkey.
Right.
Those things also just dangle and don't really move about. So from that point of view, we really just don't know. I think if we managed to get pretty close up to the specimen and didn't see anything that suggested a follicle. But in the future, maybe that's something that more fossils could help to answer, because we have a side-on view. Ideally, we also want fossils in top view, and maybe even if there's a fossil that cuts through. Can cut through the fossil. At the moment, we just don't know. But it would be neat, like if they could move. I think at the moment, from what we can say, in terms of it being similar to these three modern bird structures, and the way we see them in the fossil kind of drooping and being curved, they seem to have been quite passive.
Wow. Now, in turkeys, here at least in Texas, we look at the length of the beard as an indicator of maturity. And can you, looking at your specimen, are you able to are there any indicators that you're looking at an adult? I mean, it of course could be a new species, so it may not, but are there any indicators that would suggest that those bristles are associated with an adult?
Well, the laser kind of helps us answer, sheds light on this, because the laser, if you shine it on the bone, what the laser is doing is it's picking up on very subtle differences in the geochemistry or the chemistry of the fossil. And if you have a fossil bone, it's fossilized with a chemistry that is different to if you fossilized cartilage. So if an animal isn't fully developed, you actually see cartilage on the end of the bone. So sometimes, most of the time when you eat a chicken, you actually see caps of cartilage on the ends of the bone because that's actually, those animals aren't actually fully mature. So with our laser, we didn't see any cartilage on any of the bones. So that suggests that it's kind of more adult, and especially given its size. So that kind of is some evidence suggests that this animal's an adult, but because we're still not unsure about what species it is, or can't be confident what species it is, we can't say for sure. If we have other specimens that have, these other specimens that I mentioned that have scales, we're not sure if they are the same species as our bristle form. And because of that, we can't say if there's some sort of, if these bristles appear later in life, or if they're actually found throughout. However, looking at the bristles themselves, they actually vary. They're arranged in bundles. They actually arrange in length and in width. And there is some, that there's some indication that, we have, areas with thinner ones that are shorter, areas with longer ones that are thicker, that these might be relating to younger bristles and older bristles. So because we see that potentially suggests that there's some way for these structures go through this a growth trajectory, and they might actually like the turkey beard, as the animal gets older, they might get longer. So I think that's we can't be confident at the moment, but I think that's probably most likely what's happening, just like in a turkey beard.
Wow. So since Psittacosaurus is one of the earlier members of the ceratopsian family, do you think it's likely that it passed down to the more recent members? I guess my question is, could Triceratops have these things?
Yeah, that's a great question, because I've seen new reconstructions of Triceratops with bristles, and some with on the tail, like Psittacosaurus. Others based on what we see in Dinosaurs, which is an animal that's more primitive than Triceratops, which has them throughout the body, and even growing out of some of the scales. So in some recent reconstructions, you have Triceratops with the bristles on the tail and scales on the body with bigger scales containing more bristles. I wouldn't say that's inaccurate, because if we look at, we have an example of a primitive Ornithischian, an intermediate Ornithischian, and a more advanced Ornithischian that have it. So that kind of suggests that that these animals may have all had it. The problem is to do with how many different fossils, different species we have, how many different species have this structure. And at the moment, I think from a statistical point of view, we just don't have enough species with these structures to say with a high level of certainty that Triceratops had it. But wouldn't it be cool if it did? Because we know that T-Rex, it has ancestors that had these like hair-like structures, but obviously we've been talking a lot about how these ones in T-Rex seem to be related to true feathers rather than being different. I think because we see that in other dinosaurs, that earlier members of a group having something, the older ones should have it. There's like this precedence. Then I think it's kind of reasonable to have it. But I think to be sold with the idea and to kind of erase my childhood ideas of Triceratops, my cherished ideas of Triceratops and what it looks like, I would like to see more fossils from different parts of the Ceratopsian tree to kind of be sold.
Yeah, when the announcement of your work came out, I instantly saw every dinosaur now being bristled. It started the great.
Yeah, no, sure. Yeah, definitely. I think it's when since the 90s, since these feathered dinosaurs have come out, people have had to basically redraw all of these theropods, and certainly with ornithischians, we're starting to get the evidence to maybe rethink how we draw those. So I mean, my prediction is we've got a bit of work to do in fully studying what the fossils we have, and then we got to do a bit more get digging. And my prediction, you heard it here first, is that we might be changing a lot of ornithischians in the next 10, 20 years.
Wow. I bet every paleo artist in the world hates your work.
Yeah, they're like, well, actually, it could be the opposite. They'll be like, I've got more business now. So.
Well, that's true. All they have with yours. The good thing about bristles is all they have to do is buy a pencil and just
exactly.
draw the clumps.
It's not very hard to draw. Yeah.
It's not like they have to feather the whole thing. So maybe you'll be a hero. Well, I got to tell you, I have enjoyed this immensely, and I wanted to say, of course, and you had said at the beginning of the show of so many new discoveries. Would you consider coming back as you find more things, and would love to interview you again on some of the other projects you're working on?
Sure. Actually, speaking of Psittacosaurus, I've got a paper that's going to come out next week, and it should hit. This one's, I think, going to make a splash. It's actually talking about the color patterning of Psittacosaurus.
Oh, wow!
I can't give you too many details, but it's the first of what the paper's going to talk about. So wow. I'd be very happy to talk about any of my discoveries, and I too have enjoyed it very much, and hope that there's someone out there listening that will be a paleontologist someday.
Boy, how nice would that be? And then they could learn to run a laser and take over the world like some maniacal, some crazy madman in Hong Kong who's slicing fossils. He is from the University of Hong Kong. He is a research assistant professor, and he is the head of the Vertebrate Paleontology Laboratory in the University of Hong Kong. Dr. Michael Pittman, this has been an honor and a pleasure to work with you, and I hope we can get you back on again.
Thanks, George. My pleasure.
Well, episode 105 is done. I hope everybody enjoyed it. That interview with Dr. Michael Pittman was a lot of fun and very informative. Make sure to follow us on Facebook and Twitter when you go to my podcast page, which is dinosaurgeorgepodcast.com. You will see links to everything. Share it with your friends if you would. I appreciate that very much because the more listeners we get, the more fun it will be. Make sure to visit my online catalog at store.dinosaurgeorge for all of your dinosaur needs. Check out my website, dinosaurgeorge.com. Till next time, everybody, I hope you enjoy yourself. Have a great day. Take care of your friends and take care of the people around you. The world is so much better when we are decent to each other. I'm Dinosaur George, and I'm gone.
Thank you for listening to the Dinosaur George Show. Please follow us on our social media links and join our mailing list. If you're interested in having Dinosaur George speak at your event, please visit our website.